What if a single artifact, discovered by chance, could rewrite the entire history of technology, suggesting an ancient world far more advanced than we ever imagined? This is not the premise of a fantasy novel, but the true story of an object recovered from the depths of the Aegean Sea, an object known as the Antikythera mechanism. Hailed as the world's first analog computer, this intricate device of bronze gears and dials challenges our understanding of the capabilities of ancient Greek civilization. Its discovery in 1901 was an accident, a byproduct of a humble sponge diving expedition that stumbled upon a treasure of immeasurable historical and scientific value. The story of its finding is as dramatic as the secrets it would eventually reveal, a tale of danger, luck, and a silent shipwreck guarding its precious cargo for 2,000 years. The stage for this monumental discovery was set not in a grand library or a university, but on the barren, windswept island of Antikythera, situated between Crete and the Peloponnese in Greece. It was the spring of 1901, and a crew of experienced Greek sponge divers from the island of Symi was working the treacherous underwater reefs of the region. Their captain, Dimitrios Kontos, directed his crew as they plunged into the deep, cold water, weighed down by the cumbersome diving suits of the era. The primary goal was a commercial one: to find and harvest valuable sponges from the seabed, a perilous occupation that demanded immense courage and skill. Little did they know that on this particular day, they were about to make an archaeological find that would astonish the world. One of the divers, a man named Elias Stadiatis, descended to a depth of approximately 60 meters, a dangerous depth for the diving technology of the time. Suddenly, he resurfaced in a state of panic, frantically signaling to be pulled back onto the boat. According to some accounts, he claimed to have seen a heap of dead naked women on the seafloor, a terrifying and confusing report for the crew waiting above. Captain Kontos, suspecting nitrogen narcosis or rapture of the deep had disoriented his diver, decided to go down himself to investigate the strange vision. What he found was not a macabre scene, but something far more profound and historically significant. The sunken remains of an ancient Roman-era shipwreck, scattered with a breathtaking collection of statues and cargo. The sight that greeted Captain Kontos was a time capsule from antiquity, a vessel that had succumbed to a storm sometime around 70 to 60 BCE while carrying a luxury cargo from the eastern Mediterranean to Rome. The dead naked women seen by Stadiatis were in fact a collection of magnificent marble and bronze statues, now resting on the seabed, their forms hauntingly distorted by the deep-sea environment. Alongside the statues lay a trove of other artifacts, including fine pottery, glassware, and amphorae, all pointing to a wealthy cargo and a high-status owner. Recognizing the immense importance of the find, Kontos and his crew realized they had stumbled upon something far more valuable than sponges. They had found a direct link to the classical world. They contacted the Greek government, and what began as a commercial venture soon transformed into the first major underwater archaeological expedition in history. The subsequent recovery efforts, which spanned nearly 2 years, were perilous and remarkably advanced for their time, employing the Greek Navy and pioneering techniques for deep-water archaeology. Among the hundreds of artifacts carefully raised from the wreck were treasures like the stunning bronze statue of a youth, now known as the Antikythera Ephebi, and the philosopher's head. However, amidst these celebrated masterpieces was a far less conspicuous object, a heavily corroded lump of bronze, about the size of a small shoebox. It was split into several large fragments and encrusted with a thick, solid layer of marine sediment and calcium carbonate, which had fused it with other pieces of bronze and wood. To the naked eye, it was an unassuming, almost ugly piece of metal, and its true nature was completely overlooked in the initial excitement over the more visually stunning discoveries. Once transported to the National Archaeological Museum in Athens, the artifacts were meticulously cleaned, catalogued, and studied by the world's leading experts. The bronze statues and marble figures received immediate attention, while the unassuming bronze lump was set aside, its secrets hidden beneath a rock-like shell. For several months, it sat in a museum storeroom, considered little more than a curiosity, a concretion of miscellaneous debris from the ship's hold. The encrustation was so thick and hard that it seemed impossible to penetrate without destroying whatever might be inside. This inert, silent object held the key to a technological leap thought impossible for its era. Yet it was on the verge of being ignored, its profound significance locked away by the very sea that had preserved it. The turning point came when the lump began to dry out in the museum's controlled environment, causing the outer layer of calcite to crack and split. A small piece of the outer shell flaked away, revealing something that should not have been there: a tiny, perfectly formed gear wheel, complete with precisely cut triangular teeth. This was a moment of staggering revelation, for geared mechanisms of this complexity were not known to exist until the astronomical clocks of medieval Europe more than 1,000 years later. The find was so anomalous that some initially suspected it was a more modern object that had somehow become mixed up with the ancient artifacts. But its provenance from the securely dated wreck was undeniable, presenting scholars with an impossible historical paradox. The implications of this single gear wheel were earth-shattering for the fields of archaeology and the history of science. According to leading researchers of the time, the ancient Greeks had a sophisticated understanding of geometry and astronomy, but their mechanical technology was thought to be limited to simple machines like levers, screws, and water wheels. The discovery of a precision-engineered gear cluster suggested a completely different and highly advanced technological tradition that had been completely lost to history. Suddenly, this corroded lump was the most important artifact from the entire shipwreck, a silent testament to a forgotten genius. It was no longer just a piece of bronze. It was a puzzle that promised to redefine the technological capabilities of the ancient world. Thus began a century-long quest to unlock the secrets of the Antikythera mechanism, a scientific journey that would push the boundaries of technology itself. The challenge was immense. How could one peer inside a solidified mass of bronze and stone without destroying the delicate and priceless machinery within? Early attempts were crude and nearly catastrophic, but with the advent of X-ray technology in the 20th century, the first tantalizing glimpses of the device's internal complexity emerged. The mechanism was a complex assembly of at least 30 interlocking gears, dials, and inscriptions, a device of breathtaking mechanical sophistication. This was not a simple astrolabe or calendar, but a machine designed to model the movements of the heavens with unparalleled precision. A true analog computer from the age of Caesar and Cicero. Thus began a century-long quest to unlock the secrets of the Antikythera mechanism, a scientific journey that would push the boundaries of technology itself. The challenge was immense. How could one peer inside a solidified mass of bronze and stone without destroying the delicate and priceless machinery within? Early attempts were crude and nearly catastrophic, but with the advent of X-ray technology in the 20th century, the first tantalizing glimpses of the device's internal complexity emerged. The mechanism was a complex assembly of at least 30 interlocking gears, dials, and inscriptions, a device of breathtaking mechanical sophistication. This was not a simple astrolabe or calendar, but a machine designed to model the movements of the heavens with unparalleled precision, a true analog computer from the age of Caesar and Cicero. Upon its arrival at the National Archaeological Museum in Athens, the bronze lump was treated with far less reverence than its more glamorous companions from the shipwreck. While the Antikythera ephebe and the philosopher's head were immediately hailed as masterpieces of classical art, the mechanism was relegated to a corner as an uninteresting piece of corroded metal. It was officially recorded as a lump of bronze with some wood fragments attached, given a simple inventory number, and largely forgotten by the mainstream archaeological community. For the curators and art historians who first examined the trove, its value was not immediately apparent, lacking any discernible artistic merit or aesthetic beauty. It was, to all outward appearances, a formless and unpromising artifact, a piece of maritime debris rather than a technological marvel. The physical state of the object presented a formidable barrier to understanding. It was roughly the size of a large dictionary, broken into 4 main fragments and fused into a single, solid mass by 2,000 years of marine concretion. This outer layer, a rock-hard mixture of calcium carbonate, sand, and fragmented bronze, was effectively a stone coffin, sealing the mechanism away from prying eyes. Any attempt to physically break this shell would have certainly shattered the delicate, corroded gears within, reducing history's most important scientific artifact to a pile of scrap. Consequently, the lump sat in museum storage for months, a silent enigma whose secrets were protected by both the sea that had encased it and the sheer difficulty of its investigation. It was a puzzle that no one at the time had the tools to even begin solving. The initial scientific assessment was conducted by experts in classical artifacts, not mechanical engineers, which contributed to the early misunderstanding of its nature. Their focus was on stylistic analysis, pottery typology, and sculptural form, disciplines ill-equipped to handle an object of pure mechanical engineering. The first breakthrough was entirely accidental, occurring as the lump acclimatized to the dry, stable environment of the museum. As the water trapped within the calcite slowly evaporated, the outer shell began to contract and stress, forming a network of fine cracks across its surface. It was through one of these fortuitous fissures that the mechanism would finally reveal a fraction of its true identity. In 1902, an archaeologist named Valerio Stias was examining the artifact when he noticed something protruding from a fresh crack in the incrustation. He saw what appeared to be a circular gear wheel, a discovery so out of place that it seemed to belong to a different era altogether. The gear was small, but its triangular teeth were clearly visible and precision-cut, a feature completely inconsistent with the known technological capabilities of the ancient Greeks. Stias immediately theorized that the object might be some kind of astronomical clock, but his initial announcement was met with profound skepticism from the academic community. The prevailing historical narrative simply had no room for such a device, and many experts dismissed his theory as a misinterpretation of an artifact. The skepticism was understandable, given the historical context of technology at the time. The complex gear train, with interlocking wheels designed to transmit and modify motion, was considered a hallmark of medieval European ingenuity, culminating in the great cathedral clocks of the 14th century. The idea that such a principle was not only known, but masterfully applied over 1,000 years earlier, was a direct challenge to the entire timeline of mechanical invention. Leading physicists and historians of science argued that the ancient world, for all its philosophical and mathematical brilliance, lacked the practical engineering skills for such precision work. The discovery of the Antikythera gear suggested the existence of a lost technological tradition, a ghost in the machine of history that left no other trace. The core of the puzzle was the device's secure provenance from the shipwreck, which had been reliably dated to between 70 and 60 BCE, based on the pottery and coins found alongside it. This dating was not in dispute, which created a profound historical paradox, an impossible object found in an entirely possible and verifiable context. For a time, some theorists even suggested that the mechanism was a modern object that had fallen into the dive site, a theory quickly dismissed by the sheer depth and integration of the artifact within the ancient wreck. As the reality of the find began to sink in, the corroded lump transformed from an overlooked curiosity into the most controversial and important scientific artifact of the 20th century. It was no longer a question of if it was ancient, but how it could possibly be so advanced. Early attempts to investigate its internal workings were rudimentary and dangerously destructive. Researchers tried to probe the cracks with needles and even considered using powerful acids to dissolve the outer calcite, methods that would have annihilated the fragile bronze gears inside. The technology required for a non-invasive inspection simply did not exist. The first major technological leap came in the 1970s with the application of radiography or X-ray imaging, which allowed scientists to see the shadows of the gears within the dense concretion for the very first time. These initial X-rays, taken by British science historian Derek de Sola Price and Greek physicist Charalampos Karakalos, were grainy and difficult to interpret, but they confirmed the astonishing complexity of the internal structure. Price's pioneering analysis of those first radiographs revealed that the mechanism contained a staggering number of gears, far more than anyone had anticipated. He identified at least 30 distinct gears, arranged in a complex layered structure that hinted at a sophisticated system of calculations. By carefully tracing the outlines of the gears and their teeth, he was able to construct a theoretical model of how they might have interacted, revealing a mechanism capable of modeling the elliptical orbits of the Moon and planets. His research, published in his 1974 book, was the first major scientific publication to treat the device as a serious object of historical inquiry and laid the groundwork for all future research. He proposed that it was an orrery, a mechanical model of the solar system, but even his brilliant analysis was limited by the resolution of the available X-ray images. Despite Price's groundbreaking work, many details of the mechanism remained frustratingly out of reach. The X-rays could show the shapes of the gears, but they could not resolve the fine, almost microscopic inscriptions etched onto the bronze plates and dials, which were likely the key to understanding the device's function. These inscriptions were the mechanism's instruction manual, a user guide that could explain what the various pointers and dials represented. The technology of the 1970s could not penetrate the dense layers to read these crucial texts, leaving the device as a beautiful but largely mute machine whose full purpose remained shrouded in mystery. The Antikythera mechanism had revealed its skeleton, but its brain, encoded in the ancient Greek script, was still hidden. For another 3 decades, the mechanism remained a tantalizing but incomplete puzzle, its secrets locked away by the limitations of 20th-century technology. Researchers could see the gears, but could not count all the teeth with certainty, nor could they read the words that would explain its purpose. The corroded lump, now famous worldwide, once again entered a period of relative stasis, waiting for a new generation of scientific tools powerful enough to finally unlock its deepest secrets. It had become an icon of lost technology, a symbol of a forgotten age of scientific achievement that defied all conventional historical understanding. The world knew it was a computer, but it did not know what it computed, how it was built, or for whom. The full story of the Antikythera mechanism was still waiting to be told, a story that would require a technological leap as profound as the one embodied in the device itself. The dawn of the 1970s marked a pivotal turning point, a moment when the dormant enigma of the corroded bronze lump was finally met with a technology capable of piercing its stony shell. The primary force driving this new phase of investigation was Derek de Solla Price, a British physicist and historian of science whose fascination with the object had been growing for years. Price understood that to understand the machine, one had to think not like an archaeologist, but like an engineer, a perspective that was revolutionary for its time. His collaboration with Greek physicist Charalampos Karakalos of the National Technical University of Athens was crucial, as it was Karakalos who secured access to the necessary industrial radiography equipment. Together, they embarked on a project that would, for the first time, reveal the astonishing mechanical heart of the Antikythera mechanism. The technology they employed was radiography, a powerful form of X-ray imaging used in industrial applications to inspect the integrity of metal castings and welds. This was not the three-dimensional computed tomography we know today, but rather a series of two-dimensional shadowgraphs, each a flat, ghostly silhouette of the complex internal structure. The process was arduous and painstaking, requiring the delicate, heavily encrusted artifact to be carefully positioned and exposed to high-energy radiation from multiple angles to build up a composite picture of its contents. Each photographic plate captured a confusing superimposition of gears, shafts, and plates, a mechanical fossil trapped in geological layers of calcite. The challenge for Price and Karakalos was not just in taking the pictures, but in deciphering the chaotic, overlapping imagery they produced. As the first clear images emerged, the initial shock gave way to sheer awe at the sheer density and complexity of the gears hidden within. Where early observers had hoped for 1 or 2 wheels, the radiographs revealed a sophisticated clockwork of at least 30 distinct gears, arranged in multiple layers and driven by a single input shaft. This was orders of magnitude more complex than any known mechanical device from the ancient world. It was a labyrinth of interlocking bronze wheels that seemed to defy the established history of technology. The gears themselves were remarkably precise, with fine, triangular teeth cut at an exact angle, a level of craftsmanship that spoke of a long tradition of mechanical engineering. The shadow graphs showed a system not of simple motion, but of calculated and regulated complexity, a machine designed to perform specific, intricate mathematical operations. Among the cascade of revelations from the radiographs, one discovery stood out as truly paradigm-shifting: the presence of what appeared to be a differential gear. A differential gear is a mechanism capable of adding or subtracting two different rotational motions, a principle essential for understanding the motion of the Moon as seen from Earth. Prior to this discovery, the invention of the differential gear was attributed to the 18th century inventor James Onnes, making its appearance in this ancient Greek device a historical bombshell. Price identified a specific gear assembly where two gears drove a third, larger gear mounted on a pin that could rotate independently, the very definition of a differential. This single component suggested that the device was not merely a simple calendar, but a machine capable of modeling complex astronomical anomalies, specifically the irregular orbit of the Moon. The implications of the differential gear were staggering, as it pointed directly to the advanced astronomical theories developed by the ancient Greeks. The leading theory during the Hellenistic period to explain the Moon's varying speed across the sky was proposed by the astronomer Hipparchus of Rhodes, who lived in the 2nd century BCE. Hipparchus's model involved a combination of circular motions and epicycle to account for what is known as the Moon's first anomaly. The differential gear within the Antikythera mechanism appeared to be a physical, mechanical representation of this very theory, turning abstract mathematical concepts into tangible, spinning bronze. This suggested the device was not just a product of anonymous craftsmen, but an instrument built by individuals who were not only masters of engineering, but also intimately familiar with the cutting-edge science of their day. To transform the two-dimensional shadows into a coherent, three-dimensional model, Price and Karakalos undertook a monumental task of analysis and reconstruction. They spent months meticulously tracing the outlines of hundreds of gear fragments visible on the radiographs, measuring their diameters, and counting as many teeth as they could discern. From these fragmented data points, they began to piece together the gear trains, calculating the ratios between interconnected wheels to determine what astronomical cycles they were designed to simulate. This was a work of intellectual detective science, blending empirical observation with informed speculation to rebuild a machine that had not been seen in 2,000 years. Their final model was a theoretical map of the mechanism's internal workings, a blueprint of its lost genius. The culmination of this decade-long effort was Price's seminal 1974 book. This publication was a landmark event in the history of science and technology, providing the first comprehensive and systematic analysis of the device. Price conclusively argued that the mechanism was an analog computer, a term he used to describe its ability to perform calculations through the use of mechanical parts rather than electronics. He dubbed it a, quote, 5, a device capable of tracking the year, the 4-year cycle of the Olympic Games, and the complex motions of the Sun and Moon. The book finally silenced most of the remaining skeptics and established the Antikythera mechanism as one of the most important scientific artifacts ever discovered. Despite the monumental success of the research, the radiographic technology of the 1970s had severe limitations that left many of the mechanism's deepest secrets untouched. The most significant frustration was the complete inability to read the thousands of characters of ancient Greek text inscribed on the bronze plates and dials. These inscriptions, likely a user's manual or a description of the functions, were crucial for understanding what the various pointers and scales on the device's exterior actually represented. The X-rays could distinguish the dense mass of a gear, but they could not resolve the microscopic, hair-thin lines of corroded lettering from the texture of the bronze itself. The machine, it seemed, had a voice, but it was speaking in a language that 20th-century technology could not decipher. Without the explanatory text, the function of the device remained a subject of intense debate and educated guesswork. Price's model brilliantly explained the Sun and Moon cycles, but what of the other pointers on what was presumed to be the front dial? Did the mechanism track the motions of the 5 known planets, Mercury, Venus, Mars, Jupiter, and Saturn, as many researchers suspected? The radiographs showed additional gear trains that could have been used for this purpose, but without the labels on the dials, their specific function could not be confirmed. The mechanism remained a brilliant but largely mute machine, its skeleton revealed, but its brain, the encoded text, still inaccessible. It was like finding a supercomputer without its operating system, a powerful tool whose capabilities could only be guessed at. Further complicating the reconstruction were the ambiguities in the X-ray images themselves, which often made it impossible to get an accurate count of the teeth on each gear wheel. The precise number of teeth on a gear is fundamental, as it dictates the mathematical ratio with any gear it meshes with, and therefore the astronomical calculation it performs. In many cases, parts of the gears were obscured by overlapping components or by particularly dense patches of corrosion, forcing Price to make logical deductions to fill in the blanks. While his deductions were remarkable and largely correct, later analyses would reveal that a few of these inferred tooth counts were slightly off, leading to minor inaccuracies in his proposed model of its planetary functions. It was a testament to the difficulty of the work that even a brilliant analysis could only be as good as the data allowed. By the end of the 1970s, the world had a revolutionary new understanding of the Antikythera mechanism, thanks to the pioneering work of Price and Karakalos. It was no longer a mysterious bronze lump, but a sophisticated analog computer, a testament to a forgotten peak of Hellenistic scientific and engineering achievement. The device contained a complex gear system, including a previously anachronistic differential gear, designed to model the cosmos with breathtaking precision. However, the full scope of its capabilities, the final confirmation of its planetary tracking, and the wisdom locked within its inscriptions remained tantalizingly out of reach. The mechanism had given up its skeleton, but its soul was still waiting to be discovered. For the next 25 years, Price's model became the definitive representation of the Antikythera mechanism, a foundational text referenced by all who studied the artifact. The mechanism itself, now fully recognized as a treasure of immense importance, was placed under the guardianship of the National Archaeological Museum in Athens, a patient and silent sentinel to a lost age. The scientific world understood that a technological chasm still existed, a gap between what was known and what could be known. The tools of radiography had taken humanity on an incredible leap of understanding, but they had reached their absolute limit. The final secrets of the world's first computer would have to wait for a new millennium and a new generation of scientists armed with an even more powerful vision. The dawn of the new millennium brought with it a convergence of disciplines and a renewed determination to finally solve the puzzle that had baffled a generation. In the United Kingdom, a team led by astronomer Mike Edmonds and mathematician Tony Freeth began to form what would become the Antikythera Mechanism Research Project, or AMRP. They understood that to surpass the limitations of Derek de Solla Price's radiographic analysis, they would need a technological leap of their own. Their vision was to apply a medical imaging technology, X-ray computed tomography, or CT scanning, to the ancient artifact, creating a complete three-dimensional digital model of its internal structure. This approach promised to not only see through the corrosion, but to peel back the layers of the machine digitally, revealing every gear, every inscription, and every hidden component without ever physically touching the fragile remains. The stage was set for a second great discovery, not from the seabed, but from within the bronze itself. Computed tomography works by taking a series of two-dimensional X-ray images, or slices, of an object from hundreds of different angles as it rotates. A powerful computer then processes these slices, reconstructing them into a detailed three-dimensional volume that can be manipulated, dissected, and examined from any conceivable viewpoint. For the Antikythera mechanism, this technology was revolutionary, moving far beyond the flat, overlapping shadows of traditional radiography. The AMRP partnered with X-Tech Systems, a British company specializing in high-precision industrial CT scanning, which built a bespoke 8-ton scanner specifically for the project. This machine was capable of resolving details down to a fraction of a millimeter, fine enough to distinguish the slight variations in density between a corroded bronze plate and an incised letter etched into its surface 2,000 years ago. This was the new, more powerful vision that the mechanism had been waiting for. In the autumn of 2005, the 82 surviving fragments of the Antikythera mechanism were carefully transported under heavy guard from the National Archaeological Museum in Athens to a dedicated laboratory. The atmosphere was one of intense anticipation, a mixture of excitement and profound anxiety, as the scientists prepared to subject the priceless artifact to this intense scrutiny. Each fragment was meticulously placed on a rotating turntable within the shielded CT scanner, a process that would generate an immense quantity of data, over a terabyte of high-resolution images for the entire set. This was no longer archaeology in the traditional sense. It was a digital excavation, a non-invasive exploration into the very heart of a lost machine. As the first three-dimensional images began to appear on the computer screens, the team knew they were witnessing history being made in real time. The initial results were staggering, immediately confirming that Price's model was a brilliant but fundamentally incomplete picture of the device's true complexity. The CT scans revealed the internal structure with a crystal clarity that was simply unimaginable in the 1970s, allowing the researchers to fly through the corroded lump and inspect every component from the inside. Where Price had identified 25 gears, the new analysis quickly uncovered at least distinct gears, with evidence suggesting the complete mechanism may have contained up to 37. Entire gear trains, previously invisible or obscured in the flat X-ray images, were now mapped in 3 dimensions, revealing a mechanical sophistication that far outstripped any prior assumptions. The Antikythera mechanism was not just a complex device, it was an order of magnitude more intricate than the world's leading experts had ever conceived. But the most profound breakthrough came not from the gears, but from the text. For decades, the thousands of characters of ancient Greek inscriptions had been the mechanism's greatest, most frustrating secret. The CT scanning technology, with its ability to differentiate minute density variations, finally made these inscriptions readable. The software could digitally strip away layers of corrosion to reveal the clean, sharp lines of the original engravings beneath. For the first time, the faint, ghostly traces of etched letters, previously lost within the chaotic texture of the bronze, could be isolated, enhanced, and read with startling clarity. The machine was beginning to speak, and its words were providing the context that had been so desperately missing. The researchers were now reading the world's oldest scientific instrument's own user manual. What the inscriptions revealed was a comprehensive guide to the cosmos, written in the technical language of ancient Greek astronomy. The text was dense with information, covering everything from the names of constellations and the cycles of the moon to the intricate workings of the gear trains themselves. A particularly significant discovery was made on the bronze plates that covered the back of the mechanism, which described the function of the gear trains located directly beneath them. One passage explained how a particular gear train with a ratio of 253:1 modeled the Moon's anomalous orbit, a theory directly attributed to Hipparchus. This was the quote 9 a direct textual link between the machine's engineering and the highest level of Hellenistic astronomical science. The inscriptions transformed the device from a silent machine into a fully documented scientific instrument. Furthermore, the high-resolution CT scans provided the first visual confirmation of the brilliant mechanical solution Price had only inferred. The pin and slot mechanism, the heart of the lunar anomaly calculation, was clearly visible in the cross-sectional slices of the data. One could see the small pin on one gear meshing with a slot on another, allowing for a subtle, variable speed in the rotation that perfectly mimicked the Moon's elliptical orbit around the Earth. This was not just abstract theory anymore, it was tangible, physical proof. The mechanism was a mechanical encyclopedia, a bronze book that encoded the most advanced astronomical knowledge of its time, not just in text, but in moving parts. The marriage of Greek geometric theory with Babylonian arithmetic precision had achieved a remarkable physical form. The CT data also provided compelling evidence for the function that had tantalized researchers for decades: planetary motion. While the complex gear trains for modeling the 5 known planets are believed to have been housed in the now missing front section of the mechanism, the newly readable inscriptions on the front dial fragments confirm their presence beyond any doubt. The text explicitly mentioned the planets Venus and Saturn and described their characteristic synodic cycles, the time it takes for a planet to return to the same position relative to the Sun. Although the physical gears that perform these calculations are lost, the quote 10 on the dial itself tells us that the pointers on the front dial did indeed track the movements of the planets through the zodiac. The theoretical planetary functions, which Price could only speculate about, were now a documented reality. Decoding the inscriptions on the back dials unveiled the mechanism's astonishing predictive capabilities, particularly concerning eclipses. The large upper dial on the back of the device was identified as a Saros dial, used to predict eclipses based on the 223-month Saros cycle discovered by the Babylonians. The CT scans revealed tiny inscriptions within the dial's spiral scale, which listed specific eclipse predictions, including the month, the day of the month, and even the hour. Other inscriptions noted whether the eclipse would be solar or lunar, and sometimes even indicated the direction of the shadow. This was not merely a model of the cosmos, it was a practical tool for divining the future, a device that could turn the shadowy dance of the sun and moon into a predictable, readable calendar. Armed with this unprecedented wealth of data from the gear structures and the newly decoded inscriptions, the AMRP team began the monumental task of constructing a new, definitive model of the Antikythera mechanism. They painstakingly mapped every gear connection, confirmed every tooth count, and cross-referenced the mechanical functions with the explanatory text. In 2006, the team published their stunning findings in the journal, quote, a paper that sent shockwaves through the worlds of archaeology, history of science, and astronomy. Their model was a complete working reconstruction of the device in both software and physical form, demonstrating a level of technological sophistication that challenged the entire conventional timeline of Western technology. The collaboration between astronomers, physicists, mathematicians, and classicists had solved a 2,000-year-old puzzle. The mechanism was now understood to be a single, unified device that could track the solar year, the lunar month, the complex 19-year Metonic cycle, the 76-year Callippic cycle, the 4-year Olympiad cycle, and the 223-month Saros eclipse cycle. On its front, it modeled the irregular motions of the Sun and Moon and tracked the positions of the 5 known planets against the backdrop of the fixed stars. It was a mechanical cosmos, an analog universe in a box, built with a precision that would not be seen again for at least another 1,000 years. The voice of the Hellenistic world, long silent, was finally heard, and it spoke of a genius, a scientific curiosity, and an engineering prowess that history had completely forgotten. By the end of the CT scanning project, the question was no longer, quote, 12, but rather, quote, 13. The shift from mystery to understanding was complete, a testament to the power of interdisciplinary research and modern technology. The researchers had not just decoded a machine, they had resurrected a lost chapter of human achievement. The mechanism stood as a solitary, miraculous outlier, a technological singularity from the ancient world. But its very existence now posed a new, even more profound and haunting question about the course of history. Why was this incredible knowledge lost, and why did it take nearly 2 millennia for humanity to reinvent it? The internal gear system of the Antikythera mechanism represents a pinnacle of engineering that should not have existed in the 1st century BCE. It is a complex assembly of at least 30 bronze gears, all interlocking to perform a symphony of mathematical calculations with breathtaking precision. Modern analysis of the CT data reveals a system so sophisticated that its mechanical principles, particularly the use of a differential gear, would not be known again until the 18th century. This was not a simple orrery showing the basic layout of the cosmos. It was a dynamic, calculating machine designed to model the variable speeds and complex cycles of the heavens. The gears themselves are the silent language of a forgotten technological dialect, a physical computation of the universe. At the heart of the mechanism is the main drive axle, which would have been turned by a hand crank on the side of the wooden casing. This single input powered the entire system, a brilliant design choice that mirrored the ancient philosophical idea of a single prime mover setting the cosmos in motion. From this primary shaft, a series of gears transmitted motion through the device, their carefully calculated ratios dictating the speed of each subsequent function. This cascade of motion meant that a single, smooth rotation could simultaneously drive the calendar, the lunar phase, the sun's progress, and the eclipse prediction cycles. The engineering elegance of this unified drive system is a testament to a holistic and deeply integrated understanding of celestial mechanics. The gear train dedicated to modeling the sun and moon is the most well-preserved and understood part of the mechanism. The sun's motion is represented by a relatively simple gear train, while the moon's system is far more intricate, reflecting its more complex orbit. The core of this lunar system uses a gear train with a ratio of 253:1, a number directly derived from the work of the 2nd century BCE astronomer Hipparchus. This specific ratio is crucial because it models the moon's apogee, the point in its elliptical orbit where it is farthest from the Earth, accounting for the slight wobble in its path. The mechanism does not just show the moon moving, it shows the moon moving correctly, with all its known irregularities built into its brass heart. The true genius of the lunar mechanism lies in its solution to the moon's anomalous motion, a problem that had plagued astronomers for centuries. The moon does not orbit the Earth at a constant speed. It appears to speed up and slow down depending on its position, a phenomenon known as the lunar anomaly. To replicate this effect mechanically, the ancient engineers devised an astonishingly clever subsystem, the pin and slot mechanism. This consists of two gears mounted on the same axis but able to rotate independently, connected by a small pin on one gear that slides within a radial slot on the other. As the gears turn, this connection forces a subtle, periodic variation in the driven gear's speed, perfectly mimicking the observed acceleration and deceleration of the moon. Perhaps the most stunning component within the device is a geared mechanism that functions as a differential gear, a mechanism used to calculate the difference between two rotational speeds. In the Antikythera mechanism, this differential gear takes the rotations representing the sun's motion and the moon's mean motion and combines them to produce the phase of the moon. The gear subtracts the sun's position from the moon's, with the resulting output driving the small black and white sphere on the front dial that displays the lunar cycle. The existence of a differential gear in this ancient device is staggering, as this technology was formerly credited to James Starley in the 19th century for his use in bicycles. This single component alone represents a leap of mechanical thought that seems to defy its historical context. On the back of the mechanism, separate gear trains drive the two large spiral dials, each dedicated to the monumental task of predicting eclipses. The upper dial, known as the Saros dial, follows the 223-month Saros cycle, a period over which the Sun, Earth, and Moon return to nearly the same relative geometry, making eclipses predictable. The gear train for this dial uses a series of compound gears to achieve the necessary reduction ratio, slowly advancing a pointer along the spiral over the course of centuries. The inscriptions within the spiral's divisions, now legible thanks to CT scanning, mark the specific days and hours of predicted solar and lunar eclipses. This transformed the device from a model into a practical prognostic tool, capable of foretelling events that were often seen as omens of great importance. Beneath the Saros dial lies a second spiral, the Exeligmos dial, which tracks an even longer cycle of 669 months, or 3 Saros cycles. The purpose of this subsidiary dial was to correct a small discrepancy in the Saros cycle, as eclipses do not occur at the exact same time of day after each Saros period. The Exeligmos cycle accounts for this 8-hour drift, ensuring that the eclipse predictions would remain accurate over vast stretches of time. The gear train for this dial is linked to the main Saros mechanism, automatically advancing its pointer once for every 3 full revolutions of the Saros pointer. This layered system of self-correction reveals a level of foresight and mathematical depth that is simply extraordinary. Another, simpler but no less important gear train on the back of the device displays the 4-year cycle of the Olympiad. A small subsidiary dial would indicate the year within the cycle, naming the upcoming Pan-Hellenic Games, such as the Olympics at Olympia, the Pythian Games at Delphi, the Isthmian Games near Corinth, or the Nemean Games at Nemea. This function grounds the cosmic calculations of the machine in the tangible social and political world of its user. It shows that the creator of the mechanism intended it to be more than just a scientific instrument. It was also a calendar that integrated the movements of the heavens with the rhythms of human life. The gear ratio for this dial is a simple 4:1, driven directly from the main shaft, a straightforward but crucial piece of the device's overall utility. While the gears for the sun, moon, and eclipse cycles are largely preserved, the most complex gear trains are believed to be lost forever, housed within the missing front portion of the mechanism. Based on the mounting points, physical space, and most critically, the deciphered inscriptions on the front dial fragments, researchers are certain that the mechanism also tracked the 5 known planets: Mercury, Venus, Mars, Jupiter, and Saturn. These planetary motions would have required incredibly sophisticated gear trains to model their characteristic behaviors, especially their retrograde motion, where a planet appears to move backward against the backdrop of the stars. The surviving evidence suggests these were epicyclic gear systems, where a gear mounted on the circumference of another gear could trace complex paths, a mechanical analogy for the ancient Greek theory of epicycles. The intellectual foundation for these gear trains represents a brilliant synthesis of the 2 great astronomical traditions of the ancient world. From the Babylonians came the precise arithmetic cycles, the Saros, the Metonic, and the Callipic cycles, derived from centuries of meticulous observational data recorded in cuneiform tablets. From the Greeks came the geometric models, such as the epicycle and the eccentric circle, developed by figures like Eudoxus and Apollonius to explain the physical motions of the celestial spheres. The Antikythera mechanism is the physical embodiment of this fusion, translating abstract Babylonian numbers and Greek geometry into the tangible language of spinning bronze gears. It is a mechanical testament to a Hellenistic world where science, mathematics, and engineering were intertwined. The manufacturing precision of these gears is almost as impressive as their conceptual design. Each gear was cut by hand from a sheet of bronze, with an average of about 15 teeth per centimeter, a level of miniaturization that requires exceptional skill. The teeth themselves are not the involute shape of modern gears, but are triangular, a design that was effective for the low-speed, high-torque application within the mechanism. The entire system was housed within a wooden casing made of multiple joined boards, providing a stable and protective frame for the delicate internal workings. The craftsmanship points to a workshop that was highly experienced in producing fine scientific instruments, likely located in a major center of Hellenistic learning, such as Rhodes or Alexandria. When compared to the history of European technology, the Antikythera mechanism stands in a class of its own, a solitary peak rising from a technological landscape that would not reach a similar elevation for over a millennium. The astronomical clocks of the 14th century, like the famous clock in Prague, are publicly celebrated marvels, but their gearwork is rudimentary compared to the mathematical precision of the Antikythera device. Even the first mechanical calculators of the 17th century, invented by figures like Blaise Pascal and Wilhelm Schickard, were simpler in their logical structure. The Antikythera mechanism, therefore, is not an ancestor of these later machines, but a forgotten cousin, a member of a lost lineage of ancient analog computers. In a modern sense, the device functions as an analog computer, a term that perfectly describes its method of operation. It accepts a continuous input, the turning of the crank, and processes it through a pre-programmed set of mechanical instructions, which are the fixed ratios and arrangements of the gears. The output is a set of continuous values, the precise positions, phases, and cycles of various celestial bodies displayed on a series of dials. It is not a general-purpose machine that can be reprogrammed for different tasks. but a highly specialized instrument designed for a single, profoundly complex purpose: to simulate the clockwork of the cosmos. Ultimately, the internal gear system is what elevates the Antikythera mechanism from a mere curiosity to a world-altering artifact. The gears are the undeniable physical proof that a level of theoretical and mechanical sophistication, previously attributed only to the Renaissance, was achieved in the ancient world. Each gear, each carefully calculated ratio, and each ingenious mechanical solution is a line of code in a program written not in software, but in bronze. The internal system is the engine of the machine, the brain that made its calculations possible, and the voice by which it speaks to us across 2,000 years of silence. It is a mechanical testament to a forgotten age of genius. The internal gear system is the mechanical heart of the Antikythera mechanism, but the inscriptions etched onto its bronze plates are its soul and its voice. These faint lines of ancient Greek text, nearly obscured by 2 millennia of corrosion, are the key that unlocks the machine's true purpose and complexity. For decades, these characters remained an enigmatic whisper, tantalizing researchers with hints of their contents while refusing to reveal their full secrets. They are not mere decorative labels or maker's marks. They constitute a comprehensive technical manual, one of the most extensive scientific texts to survive from the Hellenistic world. Reading these inscriptions would be the final, crucial step in transforming the corroded artifact from a mechanical marvel into a comprehensible astronomical calculator. Initially, deciphering these texts seemed an almost impossible task, a battle against the relentless forces of time and the sea. The bronze surfaces were covered in a thick, concrete-like layer of calcified deposits, and the letters themselves were often fragmentary, worn smooth, or hidden in the shadows of the mechanism's intricate structure. Early researchers in the 20th century, like Derek de Sola Price, could only make out a few dozen characters, using magnifying glasses and clever lighting to tease out the faintest glimpses of the text. Their painstaking work revealed enough to confirm the astronomical nature of the device, but the vast majority of the information remained locked away, a silent library waiting for a key that had not yet been invented. The challenge was not just one of translation, but of physical revelation. The text was simply not visible to the human eye. The breakthrough arrived with the dawn of the 21st century, bringing with it technology that could see what no human could. The Antikythera Mechanism Research Project, a team of British, Greek, and American researchers, brought the fragmented artifacts to the National Archaeological Museum in Athens for a series of groundbreaking scans. They employed high-resolution, three-dimensional X-ray computed tomography, or CT scanning, the same medical imaging technology used to see inside the human body, but with a resolution fine enough to resolve details smaller than 1/10 of a millimeter. This process allowed them to create a complete digital 3D model of every fragment, both inside and out, effectively peeling away the layers of corrosion without ever touching the fragile bronze. For the first time, the inscriptions, which had been incised into the metal before its assembly, could be read clearly on the computer screen, even where they were buried deep inside the mechanisms. The sheer volume of text revealed by the CT scans was staggering, far exceeding anyone's expectations. Over 2,000 characters have now been deciphered, a treasure trove of information that has reshaped our understanding of the device. The language of the inscriptions is Koine Greek, the common dialect spoken throughout the Hellenistic world from the time of Alexander the Great, making it readable to modern scholars of ancient Greek. The text is dense with technical information, describing the functions of the various dials and pointers in meticulous detail, effectively serving as an instruction manual for an incredibly complex piece of equipment. This discovery confirmed that the mechanism was not a one-off prototype, but a mature, fully documented scientific instrument designed to be used and understood. On the front face of the mechanism, the inscriptions describe the grand cosmic display that was once housed within the missing front plate. The text clearly labels the pointers for the sun and the moon, and most importantly, provides the names and cycles for the 5 known planets: Mercury, Venus, Mars, Jupiter, and Saturn. The Greek names used are those of the associated gods: Hermes for Mercury, Aphrodite for Venus, Ares for Mars, Zeus for Jupiter, and Cronus for Saturn, linking the astronomical functions to the familiar pantheon of Greek mythology. The inscriptions also describe the phenomena associated with these planets, such as their speed and their stations, the points where their apparent motion against the stars temporarily stops before changing direction. This front-face text is essentially a guide to the solar system model, telling the user exactly what they are observing as they turn the crank. The back of the mechanism is covered with an even greater density of text, providing detailed explanations for the complex astronomical and calendrical dials. The primary inscriptions here are the labels for the lunar calendar and the spiral dials that track the Saros and Exeligmos eclipse cycles. Within the four-turn spiral of the Saros dial, for example, the text does not simply mark the eclipse. It provides crucial details for each event, such as the hour of the eclipse, whether it is solar or lunar, and even a letter indicating its likely visibility from a specific geographical region. This level of prognostic detail implies that the device was intended for practical use, perhaps for astrological, agricultural, or even political purposes, where foretelling an eclipse could hold immense power. The text is a sophisticated blend of astronomical data and practical annotation. A particularly fascinating set of inscriptions describes the four-year cycle of the Olympiad, grounding the celestial mechanics in the social and political reality of the ancient Greek world. The text names the specific years within the cycle, and most remarkably, lists the locations of the major Pan-Hellenic games: the Olympics at Olympia, the Pythian Games at Delphi, the Isthmian Games near Corinth, and the Nemean Games at Nemea. This feature transformed the mechanism from a pure scientific instrument into a multifunctional civic calendar, allowing a user to coordinate the movements of the heavens with the most important events in the Greek cultural sphere. It suggests the owner was a person of significant standing, for whom both scientific knowledge and participation in these elite games were important. The integration of these two worlds highlights the holistic worldview of the Hellenistic era. Perhaps the most poetic and scientifically significant set of inscriptions is a type of astronomical calendar known as a parapegma, which would have been displayed on the front of the device. This text lists the days of the year on which specific stars or constellations would first appear in the sky before sunrise, an event known as the heliacal rising. Crucially, each astronomical observation is paired with a meteorological prediction, such as the rising of the Pleiades, bring in the grapes, or the rising of Arcturus, windy weather. This practice, which dates back to the Babylonians and was common in ancient Greece, linked the cosmic clock directly to the agricultural cycle, providing farmers with vital information for planting and harvesting. The inclusion of a parapegma shows the mechanism's creators intended it to serve the practical, everyday needs of society, not just the abstract interests of astronomers. The very style of the lettering provides its own set of clues about the mechanism's origin and context. The script is a formal, professional hand, consistent with the work of a highly trained scribe rather than a casual craftsman. According to leading epigraphers, the letter forms, particularly the way certain letters like sigma and rho are formed, suggest a date of manufacture in the late 2nd or early 1st century BCE. Furthermore, an analysis of the dialect and vocabulary used in the inscriptions has sparked a fascinating debate among scholars. While Koine Greek was widespread, some specific words and grammatical constructions point towards a Doric dialect, which was prominent in the Peloponnese and on islands like Rhodes, rather than a purely Ionian dialect typical of Alexandria. This linguistic evidence has led many researchers to propose that the mechanism was not built in the Great Library of Alexandria, as was once assumed, but in another major center of Hellenistic science, most likely the island of Rhodes. Rhodes was renowned for its astronomical tradition, home to figures like Hipparchus, often considered the greatest astronomer of antiquity, who is credited with discovering the precession of the equinoxes. The engineering expertise required to produce the fine bronze gears also fits well with Rhodes's reputation as a hub of advanced mechanical engineering, particularly in the field of automata and naval technology. The inscriptions, therefore, are not just a user manual. They are a linguistic fingerprint, pointing directly to the workshop and the intellectual environment from which this astonishing device emerged. The content of the text reveals a profound synthesis of astronomical knowledge from different traditions, mirroring the design of the gears themselves. The cycles used for predicting eclipses, like the Saros cycle, are of Babylonian origin, a testament to the vast flow of scientific knowledge across the ancient world. The names of the constellations and the mythological framework, however, are purely Greek, showing how these imported numerical systems were adapted to fit a local cosmological understanding. The inscriptions explicitly named these cycles and explained their function, suggesting that the maker of the mechanism was fully aware of the diverse sources of his knowledge. The text is a written record of the intellectual fusion that made the device possible. The technical nature of the inscriptions is perhaps their most revolutionary aspect. For the ancient world to possess a functioning mechanical computer is astonishing, but for it to be accompanied by a technical text of such clarity and detail is almost unprecedented. The language is precise and unambiguous, a far cry from the more philosophical or poetic writings that dominate much of classical literature. It reads like a modern engineering document, using terms for shafts, pointers, dials, and gears with specific functional meanings. This suggests the existence of a sophisticated tradition of technical writing in the Hellenistic period, a genre of literature that has otherwise almost completely vanished from the historical record. The existence of such a manual implies the existence of a literate audience capable of understanding it. This was not a magical black box whose workings were shrouded in mystery. It was a scientific instrument whose principles could be explained in text. The manual presumes a user who has some familiarity with astronomical concepts like the zodiac, planetary motion, and eclipse cycles. This challenges the modern perception of ancient societies, suggesting there was a wider community of educated individuals who were not just philosophers or poets, but also engaged citizens of science and technology. The manual is a window into a world where scientific literacy was more highly developed and more widely valued than we previously thought. The process of reading the inscriptions continues to this day, with each new digital processing technique revealing ever more faint characters from the CT scan data. Advanced software can now flatten the 3D surface of a fragment onto a 2D plane, enhancing the contrast between the incised letters and the surrounding bronze to make them more discernible. Researchers are constantly refining their readings, correcting earlier interpretations, and occasionally discovering entire new words or phrases that had been missed. It is a painstaking process of digital archaeology, where the excavations are performed with algorithms instead of trowels, and every new character is a significant discovery that adds another piece to the puzzle. The text, once thought to be almost completely lost, is slowly and methodically being restored to the world. The inscriptions confirm the astonishing sophistication of the mechanism, but they also deepen the sense of loss surrounding its legacy. If such a complex machine warranted a detailed user manual, it stands to reason that other similar machines must have existed. What other scientific instruments were invented and documented in the workshops of Rhodes or Alexandria, only to have their creations and their manuals consumed by the fires of history and lost forever? The Antikythera mechanism may be the sole survivor of a forgotten generation of ancient analog computers. Its inscriptions are a haunting reminder of an entire scientific tradition that vanished, leaving only this single incredible artifact as proof of its existence. Ultimately, the inscriptions are what breathe life into the bronze gears of the Antikythera mechanism. Without them, the device would remain a magnificent but mute object of speculation, a beautiful puzzle with no solution. The text gives the machine a voice, allowing it to speak directly to us across 2,000 years, explaining its own purpose and revealing the intellectual world of its creators. It transforms the mechanism from a passive relic into an active teacher, a tangible link to the minds of ancient Greek astronomers and engineers. The inscriptions are the final, crucial piece of evidence that irrevocably changed our understanding of the history of technology. They are the user manual for a lost, ancient world. The inscriptions provided the ultimate user manual, explaining the mechanism's purpose and functions, but the true marvel lies in how its intricate bronze gears executed these complex calculations. This device was not merely a static calendar, but a dynamic mechanical model of the Hellenistic universe, designed to simulate and predict the movements of celestial bodies. Its primary function was to solve the ancient problem of tracking the Sun, the Moon, and the 5 known planets, Mercury, Venus, Mars, Jupiter, and Saturn, within a geocentric framework. The Greek cosmos, with the Earth at its center, was a system of nested, perfectly rotating spheres, an idea the mechanism translates into a tangible, working machine. By turning a single hand crank, an operator could set this cosmic clockwork in motion and peer into the future. The motion of the Sun, as represented by one pointer on the front dial, was relatively simple to model, achieved through a basic gear train that completed 1 revolution per year as the device was turned. The Moon's motion, however, is far more complex, speeding up and slowing down during its orbit, a phenomenon known to ancient astronomers but difficult to replicate mechanically. To capture this lunar anomaly, the ancient engineers devised a remarkably ingenious solution that points to an understanding of elliptical motion long before Kepler. Deep within the device's gear system, a gear with an off-center pin engages with a slot on another gear, a feature known as a pin and slot follower. As the main gear train turns, this mechanism causes the output gear for the Moon not just to rotate, but to oscillate in speed, perfectly mimicking the Moon's varying velocity as it orbits the Earth. This pin and slot mechanism is considered one of the most brilliant engineering feats of the ancient world, demonstrating a level of mechanical sophistication that was previously thought impossible for this era. It effectively translates the abstract mathematical concept of an ellipse into a physical, moving part, showcasing a profound grasp of kinematics. The lunar pointer on the front dial would therefore move at a rate that accurately reflected the Moon's actual journey through the zodiac, completing 1 full cycle in about 27.5 days. This accuracy was crucial, not only for the calendar, but also for the mechanism's most celebrated function, the prediction of eclipses. The complex dance of the Sun and Moon is the foundation of any eclipse, and modeling it with such precision was the first step toward achieving the device's ultimate goal. While the lunar system is a masterpiece of mechanical design, the mechanism's true genius lies in its ability to model the seemingly erratic movements of the 5 known planets. From an Earth-centered perspective, planets like Mars, Jupiter, and Saturn appear to move forward across the background stars, then inexplicably stop, loop backward for a time, and then resume their forward course. This retrograde motion baffled observers for millennia and was the single greatest challenge for any geocentric model of the cosmos. To explain it, Greek astronomers like Apollonius of Perga and later Hipparchus developed the theory of epicycles. This theory proposed that a planet moves in a small circle, called an epicycle, whose center in turn travels along a much larger circle, the deferent, around the Earth. The Antikythera mechanism is the oldest known physical application of this sophisticated astronomical theory, transforming it from a set of diagrams on a papyrus scroll into a functioning mechanical system. The central question for modern researchers has been how its creators translated these abstract epicycles into tangible, rotating gears. The answer, revealed through high-resolution CT scanning and painstaking analysis of the inscriptions, is a system of compound gear trains of breathtaking complexity. Each planet, it appears, required its own unique and intricate arrangement of gears mounted on separate carrier plates. These were not simple gear reductions, but sophisticated mechanical computers designed to generate the exact same output as the epicyclic theory, producing the characteristic speed changes and retrograde loops of each planet. For the inner planets, Mercury and Venus, which never stray far from the Sun, the gear trains were ingeniously linked to the main solar gear train, ensuring their pointers on the dial always moved in concert with the Sun's pointer. The system for Mercury in particular required an exceptionally complex train to simulate its swift and highly irregular motion, and recent research suggests it utilized a differential gear. A differential gear is a mechanism that combines the rotations of two separate input shafts to produce a variable output, a technology that was previously thought to have been invented in the 16th century. The discovery of its potential use in the Antikythera mechanism pushes back the history of this critical component by over 1,500 years. The gear trains for the outer planets, Mars, Jupiter, and Saturn, would have been similarly complex but operated on a different principle, as their motion is not tied to the sun's. Tragically, the actual gears for these outer planets are missing from the surviving fragments, likely having corroded away completely during 2 millennia on the seafloor. However, the inscriptions on the device's back cover provide an almost complete blueprint, listing for each planet the number of teeth in every gear and describing their arrangement within the system. It is from this textual evidence alone that scientists like Tony Freeth and Alexander Jones have been able to reconstruct these lost systems, proving they were just as sophisticated as the surviving lunar mechanism. These reconstructions show that the ancient engineers had solved the planetary problem with pure, unadulterated mechanics. Beyond modeling planetary motion, the mechanism's most socially significant and publicly impressive function was the prediction of eclipses, a capability underscored by the sheer amount of space dedicated to it on the back of the device. For this, it utilized a period known to Babylonian astronomers for over a millennium, the Saros cycle. The Saros is a period of approximately 18 years, 11 days, and 8 hours, after which the Sun, Earth, and Moon return to nearly the same relative geometry, making another eclipse very likely. This cycle does not produce identical eclipses, but it provides a powerful predictive framework for foreseeing when and where an eclipse might occur. The mechanism's creators adopted this Babylonian knowledge and built it directly into their machine. On the upper back of the device, a large 4-turn spiral dial was used to track this cycle, with each of its 4 quadrants representing one full Saros period of 223 lunar months. As the mechanism was operated, a dedicated pointer would advance 1 step for each new month, slowly spiraling inward until it completed the cycle, at which point it would be manually reset to the outer edge. Specific months along this spiral were marked with inscriptions, using a system of letters and symbols to indicate whether a solar or lunar eclipse was predicted to occur. These markings were not generic. They were specific predictions tied directly to the calculated positions of the Sun and Moon. The inscriptions accompanying these eclipse predictions went even further, often specifying the hour of the day when the event would occur, and even the cardinal direction the eclipse's shadow would travel. Furthermore, to correct for the fact that the Saros cycle is not perfectly exact, and its predictions drift over time, the mechanism also incorporated the exoligmos cycle. The exoligmos cycle is exactly 3 Saros cycles, or a period of 54 years, which corrects for the 8-hour discrepancy and brings the predictions back into near-perfect alignment with the actual eclipses. This combination of a long-term predictive cycle and a short-term correction factor represents a staggeringly advanced computational system for forecasting celestial events with an accuracy that would not be surpassed for many centuries. The ability to predict an eclipse was not merely an academic exercise in the ancient world. It was a source of immense political, social, and religious power. Eclipses were often seen as terrifying omens, divine messages that could signal the fall of a king, the outbreak of famine, or the end of an empire. The unexpected darkening of the sun or the blood-red moon could plunge entire cities into panic and chaos. An individual who possessed a machine that could foresee such events with apparent ease would be seen as having a direct line to the cosmos, possessing a wisdom that bordered on the divine. This knowledge could be used to command respect, allay public fear, or even manipulate political outcomes by timing events in accordance with quote 16 or quote 17 omens. This predictive capability would have been invaluable to a ruler, a city-state, or a wealthy patron who could use the information to demonstrate their connection to the cosmic order. Combined with the parapegma on the front dial, which provided agricultural and meteorological advice tied to the rising of stars, the device becomes a comprehensive tool for managing both the heavens and the earthly realm. It was a technology designed to bring order and predictability to a world often perceived as chaotic and governed by capricious divine forces. The mechanism allowed its owner not just to understand the universe, but to anticipate its will, a truly godlike power in the classical world. It was, in essence, a portable oracle powered by gears and scientific knowledge rather than by mysticism. Despite the immense detail revealed by modern analysis, some profound questions about the mechanism's predictive power and its ultimate purpose remain intensely debated among scholars. Just how accurate were its predictions over decades, or even centuries of continuous use? And were there built-in methods for calibration or correction that have since been lost? Did the mechanism's eclipse predictions account for the slight variations in visibility from different geographical locations, such as the crucial difference between an eclipse being visible in Alexandria versus Rhodes? These are not trivial details, but speak to the very practical application and intended audience of the device. Was it a broad, general-purpose tool, or a finely tuned instrument for a specific location? Some researchers speculate that the device may have been intended primarily as a demonstration piece, a showcase of mechanical and astronomical prowess created for a wealthy Roman or Greek patron to impress guests and display their intellectual sophistication. This theory posits that its primary value was symbolic rather than practical. Others, while a more fringe theory, have even proposed a connection to navigation, attempting to link its predictive powers to the needs of sailors, though the geocentric model and its complexity make this seem unlikely. Without any other surviving examples, no written records from its creator, and the complete loss of its historical context, the true story of its use, the who owned it, where it was kept, and how often it was operated, remains one of the most tantalizing mysteries surrounding the Antikythera mechanism. Ultimately, the Antikythera mechanism's ability to predict the cosmos represents a fusion of science, engineering, and philosophy that is unparalleled in the ancient record and challenges our entire narrative of technological progress. It took the abstract mathematical models of the universe that existed in the libraries and minds of Hellenistic scholars and transformed them into a dynamic, physical reality that could be witnessed with a simple turn of a hand crank. This machine was not merely a passive calculator or a static star chart. It was a working model of the Greek universe, a bronze cosmos in a box whose gears could foretell the future dance of the heavens with astonishing precision. It stands as a testament to a forgotten scientific age, a lone survivor that forces us to rewrite the history of what the ancients knew and what they could build. This incredible device did not appear in a vacuum, for it was the culmination of a vibrant scientific tradition that flourished in the centuries following Alexander the Great. The era known as the Hellenistic period, stretching roughly from the death of Alexander in 323 BCE to the rise of Rome, was a golden age of inquiry and innovation. Greek culture, language, and science spread across the eastern Mediterranean, fusing with Egyptian, Babylonian, and Persian knowledge to create an intellectual climate unlike any before. It was a world fueled by royal patronage, where ambitious rulers in cities like Alexandria in Egypt, Pergamon in Anatolia, and Antioch in Syria competed to attract the greatest minds. Within this competitive cosmopolitan environment, the theoretical mathematics of astronomy was finally married to the practical art of mechanical engineering. The evidence carved into the mechanism's bronze plates and gears points with compelling force toward a single island as its most likely birthplace: Rhodes. This Aegean island was a major maritime and commercial power, but more importantly, it was renowned throughout the ancient world as a center of astronomical and mechanical expertise. The mechanism incorporates the most sophisticated lunar theory of its time, a theory developed by the astronomer Hipparchus, who lived and worked on Rhodes in the 2nd century BCE. Furthermore, the device's calendar inscriptions include names for months used in several city-states, including the distinct Corinthian calendar. But the primary calendar appears to be that of Rhodes itself. This combination of cutting-edge astronomical theory and local calendrical data makes a Rhodian origin the most logical and widely accepted hypothesis among researchers. If Rhodes was the place, the question of the specific creator remains one of history's most captivating unsolved mysteries, although several brilliant candidates emerge from the historical record. The most frequently mentioned name is that of Hipparchus, often considered the greatest astronomer of antiquity, who resided on Rhodes for much of his career. He is credited with discovering the precession of the equinoxes, calculating the distance to the moon, and compiling the first comprehensive star catalogue, all achievements that required a profound understanding of celestial mechanics. The Antikythera mechanism embodies the very epicyclic theories that Hipparchus developed to explain the irregular movements of the planets, suggesting a direct intellectual lineage. While no surviving text explicitly credits him with its construction, the device is a physical manifestation of his life's work, making it plausible that he either designed it or inspired a generation of mechanically inclined followers. Another potential figure, though an earlier one, is the legendary Archimedes of Syracuse, who was murdered during the Roman siege of his city in 212 BCE, possibly decades before the mechanism's estimated creation. Archimedes was a master of mathematics and mechanics, famed for his inventions of war machines and his theoretical work on levers, buoyancy, and infinitesimals. Crucially, several ancient sources, including the Roman writer Cicero, describe Archimedes building a sphere or planetarium that could mimic the movements of the sun, moon, and planets. While the original device is lost, Cicero's account proves that the concept of a mechanical cosmos existed in Archimedes' mind and workshop. It is therefore conceivable that the Antikythera mechanism is not a singular invention, but a highly refined descendant of a tradition of mechanical model-making that began with Archimedes and was later perfected by his intellectual heirs in places like Rhodes. A third contender who fits the timeline and location perfectly is Posidonius, a Stoic philosopher, astronomer, and geographer who also lived on Rhodes in the 1st century BCE. Like Hipparchus, he was a leading scientific figure of his day, and historical accounts specifically state that he built an orrery, a mechanical model of the solar system, which demonstrated the movements of the sun, moon, and 5 known planets. This description aligns almost perfectly with the known functions of the Antikythera mechanism. Posidonius was also a well-connected figure who traveled extensively and corresponded with Roman leaders, which could explain how such a device might eventually find its way onto a ship bound for Rome. Whether Posidonius built the specific device recovered from the shipwreck is uncertain, but his activities prove that the construction of such complex astronomical machines was occurring on Rhodes during the precise period in which the Antikythera mechanism was made. It is perhaps more likely that such an intricate object was not the work of a single genius, but the product of a sophisticated workshop, a collaborative effort combining different areas of expertise. The construction of the mechanism would have required a team of specialists: a theoretical astronomer to provide the mathematical models, a master mechanical engineer to design the gear trains, and a highly skilled craftsman to fabricate the dozens of tiny, precisely cut gears and delicate dials. Rhodes, with its concentration of wealth, maritime trade, and intellectual talent, was the ideal environment for such a specialized workshop to exist. This model of collaborative creation would explain the sheer complexity and refined craftsmanship of the device, attributes that might be difficult for a lone individual to perfect. The mechanism could thus represent the pinnacle of a lost Hellenistic industry of, quote, 18, quote, the Greek word for both art and craft. Understanding the, quote, 19, quote, behind the mechanism is just as important as identifying its potential creator, for its purpose reveals the values and ambitions of the society that produced it. One obvious motivation was pure scientific inquiry, a desire to create a physical model that could accurately test the abstract mathematical theories of the cosmos. For an ancient astronomer, the mechanism would be an unparalleled tool for predicting celestial events like equinoxes, solstices, and eclipses, allowing them to compare theory with direct observation over many years. It transformed the cosmos from a series of abstract calculations into a dynamic, visible system that could be manipulated and understood through tangible interaction. This function aligns with the Hellenistic fascination with models and simulations, a desire to replicate and control the natural world through human ingenuity. Beyond its scientific utility, the Antikythera mechanism was almost certainly a tool for education and demonstration, a device designed to inspire awe and illustrate the mathematical order of the universe to a wealthy and educated audience. In a world without telescopes or instant communication, witnessing a small bronze box accurately predict the dance of the planets would have been a mind-altering experience. It would have been the ultimate status symbol for a wealthy patron, a Roman noble, or a Hellenistic king, a tangible proof of their sophistication and their connection to the cosmic order. The device's intricate casing and detailed inscriptions suggest it was meant to be seen, touched, and admired, a centerpiece for philosophical discussions, or a wonder to be displayed to important guests. Its value was not just in its function, but in the sheer intellectual power it represented. This leads to what was perhaps its most potent purpose in the ancient world, as an instrument for astrological and political power. The lines between astronomy, astrology, and politics were deeply blurred in the classical era, and celestial events were believed to have a direct influence on earthly affairs. An eclipse could be interpreted as a dire omen for a ruler, while a favorable planetary alignment could be seen as a blessing for a new venture. By owning a machine that could predict these events with what seemed like supernatural accuracy, its owner could claim to possess a unique insight into the will of the gods. This knowledge could be used to manage public opinion, time political announcements for maximum astrological benefit, or reinforce their own divine right to rule, making the mechanism not just a scientific instrument, but a powerful tool of statecraft. The mechanism's final journey, which ended in tragedy on the seabed off Antikythera, provides its own set of clues about its ultimate destination and purpose. The ship itself was likely a Roman commercial vessel, heavily laden with luxury goods from the eastern Mediterranean, including fine marble statues, glassware, and pottery, all destined for the burgeoning markets of Italy. This suggests that the mechanism was a valuable commodity, perhaps commissioned by or being transported to a wealthy Roman collector living in Rome or a major city like Pompeii. The Romans were known to have a great appetite for Greek art, philosophy, and technology, which they often acquired as spoils of war or through trade. The Antikythera mechanism may have been part of this cultural plunder, a masterpiece of Greek engineering on its way to adorn the villa of a Roman aristocrat fascinated by Greek knowledge. Ultimately, the creators of the Antikythera mechanism built it for a world that valued knowledge as both a path to truth and a source of power. It was a product of a unique historical moment when theoretical brilliance, practical engineering, and wealthy patronage converged to produce something centuries ahead of its time. Whether it was designed by a lone astronomer or built in a collaborative workshop, it stands as a monument to the forgotten geniuses of the Hellenistic age. They looked up at the night sky and did not just see the whims of gods, but a complex, predictable system governed by mathematics, a system they believed they could replicate in bronze and gears. Their creation was a statement of human confidence, a belief that the universe could be known, modeled, and even its future foretold. A belief that was, for a time, spectacularly realized in this astonishing machine. The discovery of the Antikythera mechanism fundamentally shatters the conventional timeline of technological history, forcing a radical re-evaluation of what the ancient world was capable of achieving. For centuries, the established narrative was one of a slow, linear progression of mechanical knowledge, culminating in the ingenious clockwork of Renaissance Europe and the scientific revolution that followed. Historical accounts of Greek technology focused on monumental achievements like aqueducts and siege engines, or on philosophical and mathematical breakthroughs, but not on complex, miniature machinery. This bronze device, however, appears as a technological anachronism, an impossibly advanced artifact dropped into a world we thought was incapable of producing it. Its existence proves that a sophisticated tradition of engineering, one that we had assumed was born over 1,000 years later, was flourishing in the 1st century BCE. The technological leap embodied by the mechanism is not merely incremental. It is a quantum jump to a level of mechanical sophistication that would not be matched until the 14th century CE in Europe. At its heart lies a gear system of breathtaking complexity, featuring over 30 interlocking bronze gears working in concert to model the cosmos. This alone is staggering, as historians previously believed that such intricate gear trains were a medieval invention. The true genius, however, lies not just in the number of gears, but in their specific and advanced functions, which solved astronomical problems with mechanical elegance. The Antikythera mechanism is not a simple orrery showing circular planetary paths. It is a dynamic calculator designed to replicate the irregular observed motions of the heavens. Perhaps the most astonishing component within this system is the differential gear, a mechanism used to calculate the difference between two rotational speeds. This specific gear assembly is employed to model the Moon's elliptical orbit around the Earth, a phenomenon known as the lunar anomaly, where the Moon appears to speed up and slow down in the sky. Before the discovery of the mechanism, the invention of the differential gear was credited to 19th century inventors who used it in early automobiles. Finding this principle so perfectly executed in a 2,000-year-old Greek device was a profound shock to the entire field of the history of technology. It demonstrates an understanding of mechanical mathematics so advanced that it should not have existed, rewriting a key chapter in the story of engineering. Beyond the differential gear, the mechanism also utilizes epicyclic gear trains to simulate the movements of the planets Mercury and Venus, which orbit the Sun. This design choice is a direct mechanical translation of the geocentric, epicyclic model of the universe first proposed by astronomers like Hipparchus and later formalized by Ptolemy. To translate this abstract mathematical concept into a working physical system required a level of theoretical and practical synthesis that is simply mind-boggling. The gear trains are not just clever, they are mathematically precise, using specific gear ratios to replicate the known orbital periods of the planets with remarkable accuracy. This proves that the Hellenistic Greeks were not only masters of astronomical theory, but also of its physical, mechanical application. The precision of the manufacturing is equally revolutionary and challenges our assumptions about ancient craftsmanship. Each gear, some no larger than a coin, was cut by hand with teeth that are not simple triangular shapes, but have a subtle, optimized profile for efficient and smooth power transfer. This indicates the use of specialized, high-precision tools, including small-scale lathes and division plates, that left no trace in the archaeological record. The craftsmanship required to create these parts is on par with that of a master watchmaker from the 18th century. The level of miniaturization and quality control suggests this was not the first such device ever made, but rather the product of a mature and well-established tradition of fine mechanical engineering. This tradition, now lost to history, represents a completely different technological path from the one taken by the dominant Roman culture of the time. While Roman engineering was magnificent in its own right, it was primarily focused on large-scale public works, roads, bridges, aqueducts, and monumental buildings. Theirs was an engineering of mass, durability, and brute force. The Antikythera mechanism, by contrast, speaks to a Greek engineering of intellect, precision, and miniaturization, where the goal was not to conquer the landscape, but to model the universe. It reveals a parallel scientific-industrial complex in the Hellenistic world, one that prized devices of intellectual power over those of civic utility. This duality of ancient technology has only now come into focus. The implications are profound, forcing historians to ask why this technology did not survive and flourish. After the shipwreck, the historical record goes silent on devices of this complexity for over 1,400 years. The astronomical clocks of Richard of Wallingford in the 14th century and Giovanni de Dondi a few decades later are considered the first true mechanical clocks of comparable complexity. yet they appear to be independent inventions. There is no clear line of descent from the workshop in Rhodes to the cathedrals of medieval Europe. This vast technological chasm is the central mystery the mechanism presents, suggesting a catastrophic loss of knowledge rather than a simple evolution. Could it be that the knowledge to create such devices was incredibly rare and concentrated in the hands of a very small number of individuals or workshops? The construction of the mechanism required a unique combination of astronomical genius, mechanical engineering prowess, and supreme metalworking skill. If this knowledge was protected as a trade secret within a single family or school of craftspeople, its loss could have been as sudden as a plague, a fire, or a conquest. A single event, like the Roman sack of a city like Rhodes or Pergamon, could have wiped out the entire lineage of masters and apprentices who held this unique expertise. The fragility of such specialized knowledge makes its disappearance tragically plausible. Furthermore, the social and economic climate of the subsequent centuries may have been hostile to the development of such specialized technology. The Roman Empire, while initially appreciative of Greek culture, increasingly prioritized practical engineering and military logistics. The market for an ultra-expensive, bespoke scientific instrument for a handful of wealthy aristocrats may have simply vanished as the economic and political landscape shifted. As the Western Roman Empire declined and the medieval period began, patronage for this kind of pure scientific inquiry would have become exceedingly rare. The mechanism may have been a beautiful intellectual luxury that the world could no longer afford or sustain. The loss of this technological branch represents a major what-if moment in human history. If this tradition of mechanical computing had continued and developed, what might the world look like today? One can only speculate whether the scientific revolution might have arrived centuries earlier, accelerating human progress in unimaginable ways. The Antikythera mechanism is a ghost of a potential future, a glimpse of a path not taken. It stands as a powerful testament to the fact that progress is not inevitable, and that vast swaths of human ingenuity can rise and fall without leaving a trace. Modern scholarship has been completely transformed by this single artifact. The history of science is no longer viewed as a simple narrative leading from the Greeks to the Renaissance to the modern world. It is now understood as a far more complex and fragmented story, filled with brilliant peaks and devastating valleys. The mechanism has forced a new generation of researchers to re-examine classical texts, looking for clues to this lost technological tradition. It has elevated the Hellenistic period from a mere footnote between classical Greece and the Roman Empire to a true scientific age in its own right, one that was capable of producing the world's first analog computer. The device fundamentally rewrites the definition of, quote, 21, quote. It replaces the image of Greeks clad in robes debating philosophy with a new image, that of a master craftsperson in a workshop, surrounded by precise tools meticulously assembling a machine of bronze. It shows that the abstract world of Greek mathematics and the physical world of making were not separate disciplines, but were deeply integrated. Theoretical knowledge was not just for scrolls and lectures, it was for gears, dials, and predictive models. This holistic approach to science and technology is one of the most important lessons the mechanism teaches. In essence, the Antikythera mechanism forces a complete rewrite of the first chapter of the history of computing. It is now recognized as the first known example of a device using a gear-based design to perform complex calculations, a principle that would underpin all mechanical calculators and computers for the next 2 millennia. It is the ancestor of Charles Babbage's difference engine and the mechanical calculators of the 17th and 18th centuries. To find this ancestor at the very dawn of the Common Era is to extend the family tree of computing by nearly 2,000 years. The history of the computer, it turns out, did not begin in Victorian England, but on a Greek island over 2,000 years ago. This technological leap also redefines our understanding of the relationship between science and society in the ancient world. The device was not just an abstract scientific tool. It was also a product of a rich, cosmopolitan, and wealthy society that valued such displays of intellectual power. It was a status symbol, a philosophical instrument, and a potential astrological tool, all rolled into one. Its existence proves that there was a sufficient level of scientific literacy among the elite to create a market for such a device. The mechanism is therefore not just a story about gears, it is a story about the social and economic conditions that can allow genius to flourish. The precision of the inscriptions, which served as the device's user manual, further highlights the sophisticated nature of this creation. The text is dense with technical astronomical information, including the cycles of the moon, the Metonic calendar, and the Saros eclipse cycle. This indicates that the device was intended for a user who was already well-versed in astronomical theory. It was not a simple fortune-telling toy for the masses, but a serious scientific instrument for the educated few. The integration of text and machine in this way is another feature that points to a highly developed and systematic approach to knowledge. The Antikythera mechanism stands as the ultimate counterargument to any notion of ancient primitivism. It is the most complex piece of scientific technology to survive from the entire ancient world, and by a huge margin. Nothing else comes close. Its discovery has forced a painful but necessary correction to our historical arrogance, reminding us that we should not underestimate the intellectual and technical capabilities of our ancestors. They looked at the same stars we do and saw not just gods and monsters, but a predictable mathematical system governed by laws they could comprehend and replicate. The sheer intellectual ambition of the device is breathtaking. Its creators did not just set out to show the positions of the sun and moon. They attempted to model the entire known cosmos, including the irregular motion of the moon and the retrograde movements of the planets. They incorporated sophisticated astronomical cycles that took decades or even centuries to observe and verify. This was an attempt to create a microcosm of the universe, a Hellenistic quote 22 rendered in moving bronze. It is the physical manifestation of the Pythagorean and Platonic ideals of a cosmos governed by number and harmony. By placing this technology in its proper historical context, we can see that it was not an inexplicable miracle, but the pinnacle of a long intellectual tradition. It builds on centuries of Babylonian astronomical observation, Greek geometric theory, and Hellenistic mathematical innovation. The mechanism is the ultimate synthesis of these streams of knowledge. It is the culmination of a journey that began with the naked-eye astronomers of Mesopotamia and ended with the master engineers of Rhodes. The Antikythera mechanism is therefore not the beginning of a story, but the glorious, tragic, and lost climax of one. The technological leap it represents was not a dead end because it was flawed, but because the world around it changed. The infrastructure that supported the Hellenistic scientific community, the great libraries, the schools of philosophy and mathematics, the wealthy patrons, was gradually eroded by political instability, warfare, and economic decline. The knowledge required to build such a device was not simple. It was a fragile ecosystem of specialized skills that required a stable and prosperous society to maintain. When that support structure crumbled, the advanced technology it produced crumbled with it, leaving no blueprint for its recovery. In the final analysis, the Antikythera mechanism rewrites history by demonstrating that the ancient Greeks crossed a technological threshold that we never knew they had reached. They invented the science of computing and the art of precision mechanics, only for both to be lost to the sands of time. The device is a lonely, silent voice from a past far more brilliant than we had ever imagined. It forces us to acknowledge that history is not a simple upward climb, but a meandering path with forgotten peaks and lost valleys, and that the greatest discoveries are sometimes those that lie buried beneath the waves of what we thought we knew. It forces us to acknowledge that history is not a simple upward climb, but a meandering path with forgotten peaks and lost valleys, and that the greatest discoveries are sometimes those that lie buried beneath the waves of what we thought we knew. The central, haunting question that follows is therefore stark and simple. Why was this technology lost? The answer is not a single event, but a convergence of powerful historical currents that conspired to sink this brilliant innovation into oblivion for nearly 2 millennia. The mechanism was not an isolated invention, but the fragile blossom of a specific intellectual ecosystem, an ecosystem that was ultimately unable to survive the storms of history. Its disappearance was a tragedy not of a single machine, but of an entire way of thinking about the universe and humanity's ability to model it. The loss of the Antikythera mechanism is the loss of a potential future, a scientific trajectory that was abruptly cut short. The knowledge required to create such a device was not recorded in a single, easily copied textbook. It was a living, breathing tradition. This tradition thrived within the great institutions of the Hellenistic world, such as the Library of Alexandria, and arguably the Library of Pergamon in modern-day Turkey, a city renowned for its scholarship and craftsmanship. These centers were hubs where astronomers, mathematicians, and master engineers could collaborate, their ideas sparking off one another to produce ever more sophisticated theories and devices. The mechanism was the ultimate product of this melting pot of Babylonian astronomical data, Greek geometry, and advanced engineering. It represented a pinnacle of applied science that depended on a stable, wealthy, and intellectually curious society to support and perpetuate it. When that society began to fracture, the intricate web of knowledge it sustained was placed in mortal jeopardy. Furthermore, the sheer economics of the mechanism likely sealed its fate. This was not a tool for the common citizen or even a typical merchant. It was an object of immense value, a luxury commission for the wealthiest of patrons, a king, or a very high-ranking Roman official. The cost of the materials, the countless hours of labor by a master craftsman, and the decades of theoretical research it embodied would have made it astronomically expensive. Such a niche market meant there were likely very few workshops capable of producing such an item, perhaps only one or two on the entire island of Rhodes. Without a broader demand or a means of mass production, the knowledge remained concentrated in the hands of a very few, making it incredibly vulnerable to disruption. If the patronage dried up or the workshop was destroyed, the technological lineage would end. The rise of the Roman Empire brought with it a profound cultural shift that deprioritized the kind of theoretical science the mechanism represents. While the Romans were formidable engineers, their focus was overwhelmingly practical and applied to the needs of the state. Aqueducts, roads, bridges, and military machines. The Greek passion for understanding the cosmos for its own sake, for modeling its mathematical elegance, was viewed with a degree of pragmatic suspicion. The Roman elite might have owned such a device as a curiosity, but they did not establish the great research institutions that the Hellenistic kings had. The intellectual climate moved away from pure science and towards administration, law, and military conquest, creating a world where a celestial calculator had less cultural relevance and fewer sources of funding. The shipwreck itself is a powerful symbol of this loss, a literal sinking of a piece of technological history into the abyss. This single vessel, likely headed for Rome with treasures to adorn a triumph or a lavish villa, became a time capsule by accident. The Antikythera mechanism on board was perhaps the only one of its kind in transit at that moment, a unique and irreplaceable cargo. Its destruction at sea meant the loss of not just the object, but a physical exemplar that could have inspired others. Had it arrived safely, it might have been copied, studied, and its principles disseminated. But instead, it became a ghost lying on the seafloor. The accident was a random, catastrophic event that perfectly mirrors the fragility of the knowledge it carried. Another grim possibility for the mechanism's absence from the historical record is the utilitarian fate that befell so many bronze artifacts in later centuries. Bronze was a precious and reusable metal, easily melted down to create weapons, tools, or coinage during times of war and economic hardship. A complex, broken device whose function was no longer understood would be a prime candidate for the crucible. In the chaotic centuries following the fall of the Roman Empire, a sophisticated scientific instrument would have had little practical value compared to a sword or a plowshare. It is entirely plausible that other mechanisms, perhaps less complex or less fortunate, were systematically dismantled and recycled, their intricate gears vanishing into the amnesia of the melting pot. This process of spoliation erased countless treasures of antiquity, and the Antikythera mechanism could easily have been among them. The philosophical and religious transformation of the late Roman and early Byzantine world also created an environment hostile to the mechanism's underlying principles. The device is a physical embodiment of a cyclical, pagan cosmos, a universe governed by the interwoven destinies of planets and stars. With the rise of Christianity, which promoted a linear view of history, from creation to judgment, such astrological modeling could be seen as irrelevant at best or heretical at worst. The focus of intellectual life shifted from understanding the motions of the heavens to understanding the nature of God and the salvation of the soul. A device designed to predict eclipses and planetary cycles may have lost its intellectual and spiritual audience, becoming a relic of a discredited pagan worldview that was actively suppressed. Crucially, the knowledge to build the machine was almost certainly a form of trade secret, passed down through a master-apprentice relationship rather than being widely published. The intricate calculations for the non-uniform motion of the planets, the ingenious design of the pin and slot mechanism, and the specialized manufacturing techniques for the tiny gears were not meant for public consumption. This kind of closed-source technology is inherently fragile, as it depends entirely on the survival of a very small group of skilled individuals. A plague, a war, a fire that destroyed a single workshop could have wiped out the entire lineage of knowledge. There was no open-source manual to be rediscovered later. The blueprint was held within the minds and hands of a few masters, and when they were gone, the secret was gone forever. The final, and perhaps most decisive, factor was the complete collapse of Western Roman civilization in the 5th century. This event shattered the very infrastructure that had supported such advanced endeavors: long-distance trade, urban centers, a literate administrative class, and the wealthy patronage system. Europe fragmented into smaller, poorer, and more violent kingdoms, where survival was the primary concern, not celestial mechanics. The specialized skills required to craft the mechanism's components were lost as the guilds and workshops that sustained them disappeared. The societal conditions that allowed a genius in Rhodes to contemplate the cosmos and build a machine to model it simply ceased to exist for 1,000 years. It was the perfect storm of political decay, economic collapse, and cultural shift that ensured the silence. Ultimately, the story of the Antikythera mechanism's lost legacy is a profound lesson in the contingency of progress. It is a stark reminder that technological advancement is not an inevitable forward-marching force, but a delicate flower that requires the right soil, climate, and care to bloom. The mechanism represents a path not taken, a scientific dead end that was not a failure of design, but a victim of historical circumstance. Its rediscovery forces a humbling re-evaluation of our own technological trajectory, showing us that the road to the modern world was not straight. It is a ghost from a past more brilliant than we ever imagined, a silent testament to the fact that knowledge, no matter how profound, can be lost forever. The story of the Antikythera mechanism, once a silent, corroded lump, has been given a second life through the dedicated work of modern researchers and engineers who have sought to resurrect its ghost. This endeavor to reconstruct the device began not with metal and gears, but with data, as early pioneers like British physicist Derek de Solla Price painstakingly analyzed the first X-ray images in the 1950s. His initial conclusions, published in a 1974 article titled "Gears from the Greeks," were nothing short of sensational, proposing a level of mechanical sophistication in antiquity that was deemed almost heretical by many of his contemporaries. Price built a working model based on his understanding, a complex assembly of gears that demonstrated the device's ability to calculate the lunar cycle. While some of his specific interpretations were later revised, his groundbreaking work was the first true attempt to reverse engineer this ancient marvel and prove its astonishing capabilities. For decades, Price's model remained the primary reference, a fascinating but incomplete representation that struggled to explain all the known functions and fragments. The true revolution in understanding would only come at the dawn of the 21st century, with the application of technology that the ancient creators could scarcely have imagined. In 2005, a team of international researchers known as the Antikythera Mechanism Research Project, or AMRP, transported the priceless artifact from the National Archaeological Museum in Athens to a specialized laboratory. There, they subjected it to high-resolution three-dimensional X-ray computed tomography, a process that could peer inside the corroded mass without causing any harm. This digital archaeology allowed them to see the individual gears with stunning clarity, count their teeth, and measure their exact dimensions for the very first time. The results of this advanced scanning were a revelation, revealing details that had been hidden for over 2 millennia and rewriting the mechanism's known complexity. The team discovered previously unknown gears, including a sophisticated differential gear system that had been hypothesized but never before seen so clearly, which was crucial for accurately modeling the variable speed of the Moon. Even more remarkably, the CT scans could detect the faint traces of inscriptions etched onto the bronze surfaces, many of which were buried under layers of corrosion and invisible to the naked eye. Using sophisticated software to enhance the contrast, researchers were able to read thousands of characters, effectively uncovering the device's user manual. These newly deciphered texts described the cycles displayed on the dials, named astronomical phenomena, and provided instructions on how to use the machine, transforming it from a mysterious object into a comprehensible scientific instrument. Armed with this unprecedented data, a new generation of reconstructions began to emerge, moving from theoretical models to tangible working machines built with modern precision engineering. One of the most prominent of these modern builders is Michael Wright, a former curator at the Science Museum in London, who spent decades studying the mechanism and created his own stunningly detailed model. Wright's reconstruction, which incorporates his own interpretations of the gear trains, includes a full planetarium on the front face, a feature he argues is strongly implied by the surviving evidence. More recently, a team from University College London, led by Professor Tony Freeth, used the CT data to create a theoretical model that they believe is the most faithful yet to the original design. Their work proposes a breathtakingly intricate system of concentric rings and gear trains to display the motions of the 5 known planets, Mercury, Venus, Mars, Jupiter, and Saturn, all from a single input drive. These modern recreations are not mere curiosities. They are powerful scientific tools that allow researchers to test their hypotheses about the mechanism's design and function in the physical world. By building a model, engineers can see if the proposed gear trains work smoothly, if the dials align correctly, and if the device is mechanically feasible with the manufacturing techniques of the 2nd century BCE. The process of building often reveals unforeseen problems or elegant solutions that were not apparent from diagrams or computer simulations alone, leading to a deeper, more practical understanding of the ancient engineer's thought process. Each successful reconstruction serves as a powerful testament to the genius of its original creator, proving that the theoretical science translated into a flawlessly executed mechanical reality. They stand as a bridge across time, allowing us to witness the cosmos as the ancient Greeks understood it, not as an abstract idea, but as a moving, predictable, and calculable machine. Yet, even with these incredible advances, the Antikythera mechanism continues to guard its most profound secrets, ensuring that its mystery endures as powerfully as its legacy. The most fundamental question remains one of identity: who was the mastermind who designed and built this astonishing device? The lack of any contemporary written account describing it or its creator is a deafening silence in an otherwise relatively well-documented period of Greek history. Some theories point to Archimedes of Syracuse, who was renowned for his mechanical inventions, though he died nearly a century before the shipwreck. Others suggest the astronomer Hipparchus, who worked on the island of Rhodes, and whose theories on the irregular motion of the Moon are perfectly reflected in the mechanism's gear trains. A more likely candidate might be Posidonius, a Stoic philosopher and polymath who also had a school on Rhodes around the estimated time of its creation, but this too remains speculative. The absence of any mention of such a revolutionary technology in the extensive writings of figures like Cicero, Plutarch, or Ptolemy is perhaps the single greatest mystery surrounding its existence. Cicero, writing about a century before the shipwreck, described a device made by Archimedes that could simulate the motions of the sun, moon, and planets, suggesting such machines were not entirely unknown. However, his description is brief and lacks the technical detail of the Antikythera device, leaving scholars to wonder if he was referring to something similar but less complex, or if the full scope of this technology was simply not widely known. Was the mechanism a unique prototype, a one-off commission for a wealthy Roman patron, which never entered broader public consciousness? Or were there others, perhaps housed in the great libraries or museums of Alexandria or Rhodes, whose records were simply lost in the cataclysms of later centuries? This leads to another tantalizing question. Was the Antikythera mechanism the pinnacle of a long-standing tradition of mechanical engineering, or was it a flash of isolated brilliance that came and went without leaving a trace? The sheer complexity and maturity of its design suggest it was not the first of its kind, implying a longer evolutionary history of less complex ancestor devices that have not survived. If a whole school of mechanical engineering existed, capable of producing such an object, it would fundamentally reshape our understanding of Hellenistic science and technology. The discovery of even a single gear from another similar device in a different archaeological context would be paradigm-shattering, confirming that the mechanism was not an anomaly. Until such a discovery is made, it remains a magnificent and profoundly lonely outlier, a singular testament to a lost technological world. The reconstruction of the front face, which likely displayed the motions of the planets, remains the most fiercely debated aspect of the device. While the rear dials, with their spirals and inscriptions, have been largely deciphered, the arrangement of the planetary display on the front is unproven, as that section of the mechanism is the most heavily damaged. The recent UCL proposal is the most detailed and compelling theory to date, using the CT data to justify a system of nested coaxial tubes and intricate gear trains to drive pointers for each planet. Their model elegantly explains how the notoriously erratic retrograde motion of planets like Mars and Jupiter could be mechanically replicated using a pin and slot mechanism, a design of stunning ingenuity. However, without more physical evidence, this brilliant reconstruction, like all the others, remains a hypothesis, a best guess at the final form of this ancient analog computer. Even the inscriptions, though extensively deciphered, continue to pose puzzles, as only a fraction of the original text has survived. The scientists estimate that the mechanism's exterior casing was covered in thousands of characters, forming a comprehensive guide to its operation and the astronomical cycles it displayed. What astronomical knowledge, what philosophical commentary, or what practical instructions were contained within the text that has been lost to corrosion and time? Perhaps the missing fragments held the name of the creator, the workshop where it was made, or even a dedication to the wealthy patron who commissioned it. Each new character recovered by the AMRP team is a victory, but it also serves as a stark reminder of how much information has been irretrievably lost, leaving us with a magnificent but incomplete encyclopedia. Ultimately, the Antikythera mechanism serves as a powerful corrective to the long-held, somewhat arrogant narrative of uninterrupted technological progress, leading from the ancient world to the modern West. Its existence forces a radical reevaluation of what is often simplistically termed the Dark Ages, revealing that classical antiquity achieved a level of technological sophistication that would not be matched for another 1,000 years. It demonstrates that the path of invention is not a straight line, but a tangled, branching bush full of cul-de-sacs and lost avenues of exploration. The mechanism is a physical embodiment of a potential future that never happened, a path of scientific and mechanical development that was cut short by the contingencies of history. It is a humbling artifact that challenges our assumptions about the past and the linear nature of human achievement. In a very real sense, the modern quest to understand the mechanism is a conversation across the centuries, a collaboration between ancient Greek genius and 21st century technology. The scientists who use CT scanners to peer inside its core, and the engineers who build working models, are all engaged in a dialogue with the anonymous master who crafted it over 2,000 years ago. They are asking the same questions about the cosmos that he did, seeking to understand its rhythms and predict its movements through the elegant language of mathematics and machinery. Each gear whose function is confirmed, each inscription that is translated, feels like a direct answer from the past, a whisper of knowledge that has survived the immense silence of the ages. This ongoing dialogue ensures that the mechanism is not a static relic in a museum, but a living, breathing subject of scientific inquiry. The device itself, with its interlocking gears and precise mathematical ratios, has been described as a form of frozen music, a physical manifestation of the Pythagorean belief in an ordered, harmonious cosmos. Its creators did not just see random points of light in the sky. They perceived a complex, predictable system governed by elegant mathematical relationships, and they built a machine to prove it. The turning of its input crank would have brought the entire universe to life on its bronze dials, a miniature, clockwork cosmos guided by the hand of its operator. It represents a pinnacle of interdisciplinary thought, combining theoretical astronomy, advanced mathematics, and precision craftsmanship into a single, unified object of breathtaking beauty and complexity. It is the ultimate symbol of the human drive to understand our place in the universe. As we stand today, watching a digital simulation or a modern reconstruction turn in silent, perfect motion, we are witnessing a resurrection, a piece of the past that was thought to be lost forever being brought back to life. The story of the Antikythera mechanism is a powerful reminder that history is not a closed book, but an ongoing process of discovery, where new tools can reveal new truths hidden in plain sight. It began with a chance discovery by sponge divers in a treacherous sea, an accident of fate that preserved this priceless treasure for future generations. Its recovery from the depths was a miracle, but its true discovery has been a slow, methodical process spanning over a century, a testament to human curiosity and persistence. The enduring mystery of the Antikythera mechanism is not just about the questions that remain unanswered, but about the very fact of its existence. It is a ghost in the machine of history, a silent challenge to our understanding of the past, and a profound inspiration for the future. It teaches us that genius can bloom in the most unexpected places, and that the greatest achievements of humanity can be as fragile as they are brilliant. The mechanism lies in the museum in Athens, no longer turning its gears, but it continues to turn the gears of our minds, forcing us to think differently about history, technology, and the boundless potential of the human intellect. It is more than an artifact. It is a story, a puzzle, and a legacy, all contained within a corroded lump of bronze that changed the world.